Hey guys, this is Mr. Kramer, and we're getting ready to start our second week of instruction. So I hope you guys are doing okay. I'm doing fine. Just doing a lot of staying at home and grading your work as you send it in to me and preparing work for the next week. Anyway, here are some reminders for you. All work is due on Monday. So please, please, please make sure that you are uploading. If you're doing Google Classroom assignments, you're uploading it. Try to upload it by Sunday night so I can get it graded. Make sure you show all your work. Please take a picture of your work and upload it and turn it in. There's a video in Google Classroom to help you with that if you need it. Third, please make sure you're watching my videos. Obviously, you're watching my video right now, so thank you. This is where you're going to find the instruction. If you have a question, you can either email me, or many of you have been sending me a comment in Google Classroom, which works great. So it's difficult for me to find these comments in Google Classroom, but I'm doing the best that I can, and I'll respond to you as soon as I can. Grades. So far, I'm taking a grade on your assignments. And either you're doing that through Google Classroom or you're doing that through the packet. So if you're doing it through the packet, then you need to make sure you're turning that packet in on Monday, completed. And the APs will get me those packets so I can grade them. And then the other grade I'm taking right now are your quizzes grades that we're doing in Google Classroom. Okay, without further delay, let's get to the notes. So you may be wondering why we are going back to this. Well, I'm trying to make this transition for you easy, and I want to make sure everybody has their technology issues dealt with before I start delving into some new material. But we will be going into new material in the next couple weeks. So this is basically some review. So when you have an exponential function and it's in this format, now notice that there's not an h and a k, or I should say they're both zeros. So there's no translations involved. Okay, so when you're in this format, and remember that investigation that we did on these types of exponential models, the A is going to represent your, yes, that's right, y-intercept. Now remember, this is true when there's no translations involved. Because in the previous video, remember, if we are moving this function around, then the y-intercept is going to change. Okay, the b value is our base, and that's going to represent our exponential rate. And the rules or conditions are, if the b value is greater than 1, we have a growth. If it's between 0 and 1, we have a decay. All right, so let's take a look at this problem. Here we have a function. Y is going to be the number of deer. X is the years since 1980. What would we know about this situation? Well, since A is the y-intercept is also known as the starting point. So we have a starting value of 350. So that means in 1980, when this began, we had 350 deer. Mr. Kramer. Yeah, there you go. 350 deer at the beginning. What else do we know? Well, since our b value is greater than 1, we have a growth, okay? And how much greater than 1 is it? Well, we're going to look at this part right here, 0.12. Multiply that by 100 because we want the growth as a percent. We get 12. So there's a 12% growth. All right, let's look at number 2. So here we have y is the number of goldfish, x is the number of number of days since Monday. What do we know about this situation? Well, we're going to have an initial number of goldfish of 75. And that's our initial amount. And notice our base is less than 1, but greater than 0. So basically, we want to subtract from 1, and we're going to have 0.08. So we're going to have a decay of 8%. All right, let's move along here. So next, we need our scientific calculator out. I put a link in Google Classroom for you to use that free one that the TI instruments are offering students. So what we're going to do right now is we're going to write the equation for this exponential function. So what do they give us? Well, they give us the y-intercept. So we're going to go ahead and start the equation out, plugging in the y-intercept in for a. Okay, and next we're going to use this point, and we're going to substitute 5 in for x and 58 in for y. Now, to save us some time, I'm going to go ahead, and the work is all in your packet, so you can see it. I'm going to go ahead and just write down the answer. So we have B is approximately 0.65, and the work is all on your paper. So our equation is going to be initial amount of 500. We have a decay of, what is that, about 35%? Quite the decay. And there is your equation. Okay, moving on. Again, this is all pretty much review for you. So let's take a look at number 2. Now number 2, we're going to do it the same way we did number 1. And this work is found in the packet. So I'm trying to keep these videos as short as I can. So let's move along here and look at another example. All right. In 1996, there were approximately 2,570 known computer viruses. By 2000, that number had risen to 34,925. Assume that the number of computer viruses is growing exponentially. Make a table of the data. Okay. So our initial amount is 2,570. And remember, when we're talking about the initial amount, we're going to use a time of 0. But we have to keep in our mind that that represents the initial amount in 1996. The initial amount. Okay, by 2000, so how many years has passed? 4 years. We have 34,925. Okay, so basically that would be the table that represents this situation. All right, write an exponential equation that models this situation. All right, so we're going to do this the same way we did number 1 and number 2 above. Substituting in our starting amount. And then we're going to substitute this point in. 4 goes in for x. And the number of computer viruses, which is y, our dependent variable, is 34,925. And then we would solve this for b. The work is on your paper. So as you can see, when we solve for b, we get 1.92, so we have a growth of 92%, and this would be the equation. Don't stop here. Remember, we're looking for the equation, so you have to put the initial amount in and then the rate. It says, according to your equation, how many viruses were there in 2005? So basically, how many years has passed? Well, we started off in 1996 and we're going to 2005. So that would be what, 9 years? So we plug 9 in for x, and then we solve for y. So we have 911,264 viruses in the year 2005. All right, last one here. According to your equation, in what year will there be 1 billion computer viruses? So we're going to have to plug in 1 billion in for y, and we're going to solve for x. So let's go ahead and work this one through together. We're solving for x, so we're going to undo the multiplication first. Okay, and when we divide, we're going to get something like, let's see if I can do this in my head, 389,105.0584. Yeah, I think that's right. Okay, equals 1.92 to the x power. Remember that when we're solving for x in the exponent in the power, we need to log both sides. And bring that x down front using the power property. And then we're going to divide by log 1.92. So we get x, and that's going to be approximately 19.73 years after 1996. So 1996 plus 19.73, we're going to be in the year 2015. See, notice it does say in what year. So you can't stop right here. You have to find out what year. So please make sure you do that. Okay, thanks for watching, and I hope you guys are safe, and hopefully I'll see you in April. We'll see.